Hey everyone, imagine this. What if, like, today was as good as it gets for medical advancements?
Oh, wow.
Yeah, bit unsettling to think about, right? But then, what if there was a chance, even a slim one, that future tech could, you know, actually fix whatever's wrong with you? Would you gamble on being preserved just in case, like revival became a thing?
It's definitely a question that's gaining traction, that's for sure. And it's fueled by, all these advancements in biostasis, the science of preserving life. And there's this new research roadmap. And it lays out this incredible, I'll be honest, little sci-fi plan to research exactly that.
And the best part is this roadmap. It's not just like pie in the sky theorizing. This is laser focused on what's scientifically possible right now within like current legal boundaries, right? No wild speculations about some futuristic society. We're talking grounded, tangible research.
Yeah, exactly. And the core idea here is to preserve the brain because it's basically the seat of your identity, right? Your memories, your personality, everything makes you you. It's almost like hitting this giant pause button, hoping that, future tech can figure out how to hit play and essentially revive the person.
Okay, so we're talking about preserving brains. Got it. But how? I mean, what are the methods they're looking at?
So there are two primary contenders, and each has like its own set of hurdles. First, there's cryopreservation, think like deep freeze using liquid nitrogen. But the real challenge is preventing those ice crystals from, basically destroying those delicate brain structures.
Yeah, that makes sense. You can't just defrost a brain like you would a steak.
Exactly.
So what's the other option?
Well, the other approach is called aldehyde fixation, and it uses chemicals to preserve the brain. Basically, what it does is it locks those intricate structures in place. Think of it as like a biological pause button at a molecular level, almost like how scientists have preserved specimens for centuries, but way more advanced.
Hold on. So we're talking about like halting decay at a molecular level.
Yes,
That's incredible, but I mean, wouldn't that like drastically change the brain?
that's the big question. And you're right, while aldehyde fixation is great at preserving the brain's physical form, it does actually alter its biomolecular makeup, which poses a huge challenge if we're talking about, reversing the process for revival. That's a puzzle for future technology to solve.
So two very different approaches, each with its own pros and cons. But what I find fascinating is that this roadmap, it breaks down this entire biostasis challenge into distinct phases, almost like, a relay race against time.
Oh, that's a great way to look at it. And you're right, time is everything in biostasis. Every minute after, the heart stops, the brain starts deteriorating. So this roadmap, it lays out this clear plan and it begins with like the pre-cardiac arrest phase.
And here's where things get really interesting, right?
Yeah.
Because it's not just about what happens after someone is like declared legally dead, but it's about their health before. Things like pre-existing conditions, the medications they were on, even their diet. It all factors into how effective these preservation techniques will be.
Absolutely. It's just like any medical procedure. The patient's overall health plays a huge role in the outcome, which naturally leads to some, complex questions about who would even be a candidate for biostasis in the first place.
Yeah, and once legal death is declared, the clock really starts ticking.
Yeah.
This is where the roadmap's next stage comes in. Post-cardiac arrest stabilization.
Exactly. And so the goal here is to basically minimize further deterioration. Imagine, like, a specialized team on standby, ready to spring into action the moment legal death is declared. And their entire mission is to stabilize the brain and prep it for long-term preservation.
It sounds like a very, carefully choreographed medical ballet where every second counts.
Yeah. Timing is everything. Even delaying by hours can significantly impact how successful any preservation method will be. It really highlights the need for immediate action.
So speed is key. The faster you can stabilize the brain, the better the chances of successful preservation.
Yeah.
Then comes the decision, right?
Right.
Cryopreservation or aldehyde fixation, which brings us to, the next hurdle, figuring out the right preservation compounds and procedures.
Precisely. And that's where this roadmap, dives deep into the science, examining each approach in like meticulous detail. So let's start with cryopreservation. Aside from the rapid cooling, one of the biggest challenges is making sure those cryoprotectants, those are the chemicals that prevent the ice crystals, can actually get to where they're needed, and that's inside the brain.
But isn't the brain a bit like a fortress, though? We have the blood-brain barrier, right? How do we get past that?
You're right, the blood-brain barrier, it's really good at its job, keeping those harmful substances out. But in this case, it also makes it really tricky to get those beneficial cryoprotectants in.
Yeah, it's got to catch 22, right?
Yeah, one of those good for the brain, not so good for biostasis situations.
Exactly.
Well,
So How do researchers get around that? We can't just, like, ask the blood-brain barrier to politely step aside.
Right. No, not quite.
Yeah.
But researchers are exploring some pretty ingenious solutions, I gotta say. One avenue is like using certain chemicals or even like focused ultrasound to temporarily make the blood-brain barrier more permeable.
Okay.
So it allows those cryoprotectants to kind of slip through.
Well, that's pretty clever. Sneak it in while the barrier isn't looking.
Exactly.
But okay, so let's say we get those cryoprotectants in. Aren't they, like, potentially harmful themselves?
That's another piece of the puzzle. You've hit on a really crucial area of research, and that's finding that sweet spot, a cryoprotectant cocktail that's effective at preventing ice damage, but also like minimizes any potential toxicity to those precious brain cells.
So a balancing act, essentially preventing one type of damage without, introducing another.
Exactly.
What I thought was interesting is this roadmap mentions how, like, nature has a few tricks up its sleeve already when it comes to, like, surviving freezing temperatures.
It's true. Some animals, like certain species of frogs, have these natural antifreeze proteins that let them withstand freezing.
Wow.
And researchers are studying those proteins, looking for inspiration to, create synthetic versions that could be incorporated into those cryoprotectant cocktails.
So we're taking cues from, like, frogs that freeze solid? It's like having, like, nature as our research assistant.
Exactly.
Okay, so that's, like, cryopreservation, some of the
Ah,
challenges there.
yeah.
What about the aldehyde fixation process? Any hurdles there?
Well, with aldehyde fixation, the delivery is less about like bypassing barriers and more about making sure that fixative solution, which typically contains formaldehyde or glutaraldehyde, it's about making sure that's evenly distributed throughout the brain.
Okay.
That ensures those intricate structures are, locked in place effectively.
Formaldehyde's been used to, like, preserve specimens for, ages.
Right.
Seems like we'd have that part figured out by now.
You'd think so, right. But there's always room for improvement. One area of focus is like optimizing the speed of the fixation process. Because the faster it happens, the better the preservation, especially in those hard-to-reach areas, deep within the brain.
So it's like we need the fixative to set in a flash, almost.
Yes.
And capture everything perfectly in place.
Yes.
But, okay, even if we perfect the delivery and the speed, there's still that question of, like, reversibility.
Right.
How do you unfix a brain?
Ah, yes, the million-dollar question.
Right.
And that's the big if with aldehyde fixation, right? While it's stellar at preserving structure, reversing those chemical changes is a monumental task, and it's a challenge that current technology really hasn't cracked.
So it's a bit of a leap of faith, right? Hoping that, like, future tech can pick up where we leave off.
Yeah.
And this roadmap, it emphasizes the need for, like, objective ways to measure how well these preservation techniques are actually working.
Absolutely. I mean, it's one thing to preserve our brain, but it's another to know for sure that we're doing it well. So this roadmap, it highlights the need for standardized, quantifiable metrics to assess the quality of the preservation.
So no more just, like, eyeballing it under a microscope and hoping for the best.
Yeah, no more of that. We need to move beyond those subjective assessments, right? And this roadmap really pushes for, like, quantitative data, measurements that let us compare different techniques and even individual cases objectively.
Okay, so what kinds of things are we measuring? Like, give me the specifics.
Okay, so on a structural level, it's about analyzing how well those connections between neurons, the synapses, those are preserved. This might involve really sophisticated microscopy techniques, maybe even mapping the brain's entire wiring diagram, what's called the connectome.
So it's not just about keeping the brain cells intact. It's about keeping them, like, wired correctly.
Exactly. Those connections are the pathways of our memories, our experiences. And then we also need to look at the preservation of biomolecules. So that's proteins, lipids, all those essential building blocks of life.
Because if those building blocks are damaged, then the brain's overall integrity is, like, compromised.
Precisely. And determining, like, a universal standard for good biomolecular preservation, that's going to be crucial, especially if we're aiming for revival in the future.
This all sounds incredibly complex.
It is.
How do you even begin to, like, measure something like the integrity of a brain's wiring?
It's a massive undertaking, and that's why this roadmap is so important. It's about defining the challenges really clearly so research can focus on, like, the right areas. For example, in cryopreservation, researchers are looking at ways to assess the quality during the process itself.
Oh, wow. You mean, like, real-time monitoring?
Exactly.
Like a quality check as the brain is actually being cryopreserved.
Yes, exactly. They're exploring things like CT scans, which can track how those cryoprotectants are distributed, and it makes sure that no ice crystals are forming during that cooling process.
It's like having this like built-in early warning system to catch any problems before they become, major issues.
Exactly. The goal is to prevent damage, not just try to fix it after the fact. And they're even looking at ways to evaluate how well the brain bounces back after being warmed up from cryopreservation.
So it's about making sure that, if we can preserve the brain, it's actually in a state where it could potentially be revived.
Yes.
This roadmap really drives home that preserving the brain, it's only half the battle.
You hit the nail on the head. Preserving the intricate structure and function of the brain, potentially for centuries, that's a whole other challenge.
Okay, so let's talk about long-term storage. We're talking about keeping brains intact for potentially hundreds of years.
Mhm.
What's the game plan?
So the roadmap outlines two main approaches: cryogenic storage and fluid preservation. Cryogenic storage, that's what most people think of, the ultra-low temperatures of liquid nitrogen,
Right.
which essentially just hit pause on all biological activity.
It's like tucking the brain in for a very long nap.
In a way, yeah. But even with something as, established as liquid nitrogen, there are still questions, right? For example, there's research going on into whether storing brains at slightly warmer temperatures, what they call intermediate temperature storage, might actually be better in the long run.
Way warmer. I thought freezing things was all about going as cold as possible.
It's counterintuitive, but it turns out those super low temperatures of, liquid nitrogen, they can actually cause stress and microfractures in the brain.
Like the brain is literally cracking from the cold.
Exactly. So intermediate temperature storage, it's about finding that Goldilocks zone, not too hot, not too cold, right?
Yeah.
To minimize that stress and prevent any additional damage. But it is a balancing act because this method is more complex and more expensive to, maintain over time.
And what about this fluid preservation method? What's the thinking there?
So fluid preservation involves storing the brain in a specially designed solution, and this is typically done at temperatures above freezing. The idea is that the fluid helps maintain the structural integrity of the brain and prevent degradation.
Okay, so no deep freeze required.
No deep freeze.
It's always a catch, right?
Mhm.
So what's the catch with this one?
The biggest challenge with fluid preservation is ensuring the stability of that fluid over potentially centuries.
Oh, wow.
And it's still a relatively new area of research, so its long-term viability is still being investigated.
So it's a bit of a gamble compared to cryogenic storage, which has like a longer track record, so to speak.
That's a fair assessment. But fluid preservation does have some potential advantages. It's generally less expensive, it requires less energy, and it might even be less vulnerable to things like power outages.
Interesting. So it's less about like freezing time and more about creating the like perfect chemical cocoon.
Exactly. Ultimately, choosing between cryogenic storage and fluid preservation will come down to a really complex set of factors, including things like cost, accessibility, and even the ultimate goals of, the biostasis procedure.
Right, because if you're signing up for this, you want the best possible chance of success, whatever, success looks like in that context. Which brings us to like the final, and I would argue the most mind-blowing part of this roadmap. How do we bring someone back?
This is where we move from preservation into the truly uncharted territory of revival. And the roadmap, it outlines three potential pathways. There's reversible cryopreservation, molecular nanotechnology, and then whole brain emulation.
Okay.
Each one pushes the boundaries of, what we even consider possible.
Okay, so break it down for me. Let's start with reversible cryopreservation. Is that just a fancy way of saying like defrosting the brain?
It is defrosting, but with, a whole lot more nuance.
Okay.
The goal is to warm a cryopreserved brain back up without causing any damage.
Okay.
And while it's still a long way off, there have been some promising successes with, smaller organisms and tissues.
Those brain slices that we talked about earlier.
Exactly.
So that's a step in the right direction.
Absolutely. And this roadmap highlights some really cutting-edge technologies that are being explored to make that rewarming process safer and more precise.
Okay. Such as?
Such as dielectric warming, which uses electric fields for more even heating. And there's also nano-warming, which uses magnetic fields to target nanoparticles within blood vessels.
Okay.
So it's really targeted.
So it's not just about thawing out. It's about thawing with like incredible precision.
Exactly, because even tiny ice crystals forming during rewarming can cause irreparable damage. So it's a very, very delicate dance between cold and warmth, and we're still learning the steps.
Okay, so that's reversible cryopreservation. What about molecular nanotechnology? That sounds straight out of science fiction.
It does. So we're talking about like microscopic robots,
Yeah.
nanobots, that could theoretically go in and repair damage at a cellular level, even rebuild damaged structures. It's like having a microscopic repair crew for your brain.
That's incredible.
Yeah.
And while that might sound like pure science fiction, there's like serious research being done in nanotechnology.
Yes, yeah.
And some experts, they believe that it could hold the key not only to reversing the damage caused by, cryopreservation, but also to tackling like aging and disease.
It could. It's a fascinating, fascinating field.
So it's not just about reviving people who have been, cryopreserved. This could like revolutionize medicine as we know it.
It could. The long-term potential of molecular nanotechnology is vast, but we need to, acknowledge where we are now, which is still in the very early stages.
Right.
We're not talking about nanobots cruising through our bodies anytime soon.
Okay, so we've got bringing the brain back to life and repairing it with like tiny robots.
Yeah.
What's that third option for revival?
So that would be whole brain emulation, arguably the most ethically and scientifically complex path of the three.
Okay, we've danced around it long enough.
Yeah.
What exactly is whole brain emulation?
Okay, imagine scanning a preserved brain in such detail that we could create a working simulation of that person's mind, but on a computer.
Okay, so essentially like uploading someone's consciousness to a digital realm.
Yeah.
That's some serious Matrix level stuff.
You're not wrong. It's a simplified way to think about it, but you're not wrong.
Right.
However, there are some significant philosophical and technical challenges.
Like what, it seems like if you can like map the brain,
Right.
then we should be able to recreate it digitally.
You would think so, right?
Yeah.
It's not quite that simple, unfortunately. For starters, we need to be able to map the brain down to the level of individual synapses, those connections between neurons, and that in itself is a monumental task.
Right. And even if we manage to do that, there's still no guarantee that we could actually recreate consciousness, right?
That's exactly it. That's the crux of the debate. The mind, it's more than just the sum of its parts.
Right.
It's about subjective experience, consciousness, things that we don't fully understand yet and certainly don't know how to replicate.
So even if we created like a perfect replica, it wouldn't be the same as the original.
Exactly.
Huh. Makes you really think about what actually defines consciousness.
It's a profound question, and some experts, they believe that even like a flawless simulation wouldn't possess true consciousness in the same way that a biological brain does. And then there are the ethical implications on top of that.
It's true. The ethics are complex. I mean, what gives us the right to, like, upload someone's consciousness, even if we could?
Exactly. And this roadmap, to its credit, doesn't shy away from those ethical complexities. It acknowledges that whole brain emulation, even if it becomes possible, raises all sorts of questions about identity, personhood, consent, questions we need to really grapple with as a society.
It's bigger than science. It's about redefining what it means to be human in a world where consciousness could exist digitally.
Yeah.
This roadmap has taken us from the very tangible aspects of preserving the brain to these really mind-bending possibilities of revival.
And that's what makes biostasis research so compelling. It's at the intersection of like science, technology, and ethics. It's really pushing the boundaries of our understanding of life itself.
And the best part is, even if we don't achieve the seemingly impossible, like full-blown revival, the research being done could revolutionize other fields.
Absolutely. Imagine the implications for organ transplantation if we could just like perfectly preserve organs for extended periods. Longer wait times would be a thing of the past.
We touched on this earlier, but it bears repeating. The benefits of this research extend far beyond just that primary focus on biostasis. It's this incredible springboard for medical innovation, really across the board.
It is. The knowledge gained from figuring out how to preserve a brain could very well lead to breakthroughs in treating brain injuries, from strokes to, traumatic injuries.
The possibilities are, like, endless. This roadmap is like a launch pad for so many incredible avenues of research.
It really is. It's about asking bold questions, exploring uncharted territory, and, in the process, potentially changing the future of medicine as we know it.
And on that note, it's time to wrap up our deep dive into the world of biostasis. From cryopreservation to nanobots and the very nature of consciousness, it's been quite a journey.
It has. Until next time, keep those brains buzzing.
So we're talking about like microscopic robots, nanobots, going in and repairing damage at like a cellular level,
Hmm.
even rebuilding like damaged structures.
Yeah.
It's like having a microscopic repair crew for your brain.
It's a fascinating concept, and while it might sound like, pure science fiction, there's serious research being done in nanotechnology, and some experts believe it could hold the key not only to, like, reversing the damage caused by cryopreservation, but also to tackling things like aging and disease.
Wow. So it's not just about reviving people who've been cryopreserved. We could be talking about like potentially extending lifespan and health in general.
Yeah, it could revolutionize medicine as we know it.
It could. It really could. Okay, so we've got bringing the brain back to life, repairing it with like tiny robots. What's that third option for revival?
The third option is whole brain emulation, probably the most ethically and scientifically complex of the three.
Okay, so we've danced around it long enough. What exactly is whole brain emulation?
Okay, so imagine scanning a preserved brain in such detail that we could create a working simulation of that person's mind, but on a computer.
So essentially uploading someone's consciousness to like a digital realm. That's some serious matrix level stuff.
Yeah, it is, and it's a simplified way to think about it, but
Yeah.
there are significant philosophical and technical challenges with this.
Like what it seems like if we can map the brain, we should be able to just recreate it digitally.
You'd think so, right? It's not quite that simple, unfortunately.
Oh,
For starters, we need to be able to map the brain down to the level of individual synapses, those connections between neurons, and that in itself is a monumental task.
and even if we manage to do that, there's no guarantee that we can actually like recreate consciousness.
Right. That's the crux of the debate, right? It's more than just the sum of its parts. It's about the subjective experience, consciousness, things we don't fully understand yet, and certainly don't know how to replicate.
So even if we create a perfect replica, it wouldn't be like the same as the original. It makes you think about what actually defines consciousness.
It's a profound question, and some experts believe that even like a flawless simulation wouldn't possess true consciousness in the same way that like a biological brain does. And then on top of all that, you have the ethical implications.
Yeah, it's true. The ethics are complex. I mean, what gives us the right to like upload someone's consciousness even if we could?
Yeah. Exactly. And this roadmap, to its credit, it doesn't shy away from those ethical complexities. It acknowledges that whole brain emulation, even if it becomes possible, raises all sorts of questions, about identity, personhood, consent, questions we're going to need to grapple with as a society.
Yeah, for sure.
Yeah.
It's bigger than just science at that point. It's about redefining what it means to be human in a world where consciousness could exist digitally.
Wow. This roadmap has taken us from the very tangible aspects of like preserving the brain to these really mind-bending possibilities of revival.
It has. And I think that's what makes biostasis research so compelling. It sits at the intersection of like science, technology, and ethics, really pushing the boundaries of our understanding of like life itself. And the best part is, even if we don't achieve the seemingly impossible, like full-on revival, the research being done right now could revolutionize other fields.
Absolutely. Imagine the implications for like organ transplantation if we could perfectly preserve organs for extended periods. We'd be saying goodbye to those long wait times.
We touched on this earlier, but it bears repeating. The benefits of this research, they extend so far beyond just that primary focus on biostasis. It's like this incredible springboard for medical innovation, across the board.
Totally. The knowledge gained from just figuring out how to preserve a brain could very well lead to breakthroughs in treating brain injuries from strokes to like traumatic injuries.
The possibilities seem endless. This roadmap is like a launch pad for so many incredible avenues of research.
It really is. It's about asking these bold questions, exploring this uncharted territory, and in the process, potentially changing the future of medicine as we know it.
It's inspiring, in a way. Well, on that note, it's time to wrap up our deep dive into the world of biostasis. From cryopreservation to nanobots, and even just like the nature of consciousness, it's been quite a journey.
It has. Until next time, keep those brains buzzing.